In the last lesson, we introduced the deterministic data flow paradigm, which is a really nice paradigm for concurrent programming because it's deterministic. In this lesson, we're going to show you with some practical examples some interesting programming techniques that you can use in this paradigm. So we're going to start with a very basic and interesting technique called concurrency transparency. What this means is that you can take any functional program and add threads at will wherever you want, and the result of the program will not change. The only thing that happens is that the program becomes more incremental. Concurrency removes roadblocks, possible places where the program needs to wait. So that's the first thing. The second thing is we're going to build a for loop abstraction that collects results. So this is like a for loop where you have a calculation that is repeated, but inside each iteration you can collect results, and this will let you build concurrent agents because these collected results are put on an output stream. Now the interesting thing about this abstraction is that it's built using cells. So we're going to use mutable state to build a deterministic data flow abstraction. And you don't see from the outside that it's using mutable state, but you need mutable state internally to build the abstraction. So that's the second example. Third example, in fact, there's two examples of multi-agent programming. There is first the sieve of Eratosthenes. So this is an example where you have a stream of integers and you remove multiples in order to have a stream of primes. So the interesting thing about this example is that you're dynamically building a pipeline of concurrent agents. So you don't know in advance how many concurrent agents you need. It's only known during the execution. So this is an example of concurrent deployment where you're building the structure of the program, the agents and their connections, at the same time that you're executing the program. And this works very well in the deterministic data flow paradigm. That's one example. The next example is digital logic simulation. We're going to simulate digital logic circuits, and deterministic data flow is a very nice paradigm for simulating digital logic circuits. And the interesting thing about this example is that it uses higher order programming together with the deterministic data flow to structure the program. And you'll see how nice and simple it is to use higher order programming, which works very well together with deterministic data flow. And finally, we're also going to talk a little bit about the semantics. So we're going to extend the abstract machine to give the semantics of threads. So the basic idea is very simple. There will be multiple semantic stacks, one for each thread, and at each step, one instruction on any semantic stack is taken and executed, one step, one semantic rule. This is called interleaving semantics, and it's the simplest way to make semantics for concurrent programming. So now we're going to start with concurrency transparency. So let's now take a look at an important property of deterministic data flow. So in the last lesson, we saw that multi-agent programs are deterministic. That means if you give the same inputs, they always give the same outputs. The agent trans, if you give it 1, 2, 3, it always outputs 1, 4, 9. Okay? Now, the non-determinism that's inherent in the concurrency, where the scheduler is choosing which thread to execute at which moment, it's not observable. You always see the same result. So what this also means, if you think about it, is that concurrency does not change the result, but only the order in which computations are done. That is, when the result is calculated. And in fact, this is very strong because we can add threads at will to a program without changing the result, as many as we want. This is called concurrency transparency. The only effect of adding the threads is that the program becomes more incremental. It calculates things piece by piece. We can also see that it removes roadblocks. Notice this is true only of declarative paradigms. It's not true when we use cells and threads together. So here's an example. So this is a simple map function that takes a list and a function and applies the function to all elements of the list. Okay, it has a case and it will do f of x for every element. Now let's make this concurrent. Let's now add a thread end to the f of x. F of x will now be calculated in its own thread. Each time, each recursive call for each element x, we will create a new thread. So what's the effect of this? Well, first of all, notice this is very easy to write because the thread end can be used as an expression. F of x is an expression. We can really put it anywhere we want. Now, let's execute this program. Let's execute as follows. Let's call CMap with the arguments list 1, 2, 3, 4, and a function f which we don't know yet. So what's going to happen now? What's going to happen when we execute this? Well, we will execute something, even though we don't know the result. The browser will display a list of 4 unbound variables. So what's really going on here? Well, in fact, the input list 1, 2, 3, 4, the case statement will just traverse it as normally. And whenever it wants to calculate f of x, since f is unknown, the calculation will block. But it will block inside the new thread. So the thread executing the CMap will not block. Okay, so we will actually get an output, a list 1 with unbound variables. All the new threads, so there's 4 new threads in here, for each unbound variable here, they will all wait until f is bound to some function. Now, what would happen if we wouldn't have this thread end? What would happen if f of x would not be in its own thread? Well, in that case, the thread that's actually executing CMap would block right here. And in fact, we would never even get to do the browse. We would block inside of CMap, so nothing would be displayed. So you see, the effect of adding the thread is to let the execution go a little bit farther with the information we have. So we know the output is a 4-element list, even though we don't know the values yet. Now, let's continue execution. What happens now when we bind f, the function? A function that takes an argument x and returns x plus 1. Well, then the calculation will continue, and the browser will display the final result, which is 2, 3, 4, 5. Notice that with or without the thread creation around the fx, the result will always be 2, 3, 4, 5. If we would have not created the thread around f of x, then binding f would have also given 2, 3, 4, 5. It's just that creating the thread allows to do a little bit more, allows to go farther with the information we have. Remember, we had a list of 4 unbound variables. So the calculation is more incremental. So this leads to an approach for concurrent programming, which I call concurrency for dummies, because it's so easy. Threads can be added at will to a functional program without changing the result. So it's very easy to take any functional program and make it concurrent. You just add thread end wherever you want concurrency, wherever you want the calculation not to block, not to have a roadblock when things are not bound. A simple warning here, of course, this only works in a declarative paradigm. It does not work if you have cells. It will not work in Java. In Java, concurrency is handled with a concept called a monitor. And a monitor is a concept that coordinates how multiple threads will access an object, so the shared state. This is much, much more complicated than deterministic data flow. So concurrency for dummies only works in a declarative paradigm. So a little more deeper explanation of why it works. So here's a good old Fibonacci with 2 recursive calls. Notice I have put the recursive call, the first one, in its own thread end. Now what happens? Well, this will make the Fibonacci concurrent. It will create many threads, but the result will not change. Why will it not change? Well, let's write it in kernel language and then we see. We have here f1, which is the result of this fib x minus 1 call, and then we return f1 plus f2. Notice the only effect of the thread end here is to change when the fib x minus 1 is calculated. It does not change the value. And this connection between the creation and the use of f1 will stay the same. It doesn't matter when it's calculated. Because f1 is only bound to one value, the value will still stay the same. So, for example, here's an execution of fib 6 with very many threads created. I start here with a fib 6, and then I create a thread here to start doing fib 5. Fib 4 is calculating in the same thread as originally. Fib 4 will now create a new thread for fib 3, and fib 2 is in the same thread, and so on. And each horizontal line here is a single thread. So there are a total of 1, 2, 3, 4, 5, 6, 7, 8 threads running when I do fib of 6. And you can actually see some statistics of this in the Mozart system. There is a tool called the compiler panel, which you can activate in the Oz menu. This can tell you how many threads have been created since the system startup. Now, if you start running fib with several different arguments, you very quickly get very large numbers of threads. But that is not a problem. Threads are tools for removing roadblocks, making programs more incremental. You should not be afraid of using threads, and the system should be designed so that threads are cheap and so that they can be used in this way.